video I will present a corollary to USA 2008 problem 6. Firstly, we'll have a look at the statement. Given n persons, some of whom may know each other, we shall prove that you can put these persons into two separate rooms such that everyone knows an even number of persons in his own room. This is a very difficult combinatorics problem. So in this video we concentrate on getting the viewer to understand a solution intuitively. To complement this, we also uploaded a full PDF on our website that you can also find in the description. We consider the graph theoretic interpretation for this problem. So think of these persons as nodes in a graph. I'm drawing an example graph right here, and some of them know each other, and if two people know each other, we draw an edge between them. So for instance, this graph could look something like this. Now we want to prove that it is possible to partition this set of vertices into two sets such that the induced subgraph induced by each partition of the vertices has even degree vertices. In case all vertices have even degree, this problem is very easy because we can just put all of the persons into one room, and this indeed gives us a solution. Otherwise, it is not so easy because we have to deal with those vertices that have odd degree. But if a vertex has odd degree, it has a very nice property that we are going to try to use in our proof. Imagine if this graph right here didn't have this vertex v right here. So if we remove that, then we could try to find some solution in the remaining graph and would try to put an v back again to construct a new solution. So if we find a partition of those vertices except for v where our condition holds, then of course, since v has odd degree, there's going to be one of those sets where v knows an even number of other vertices. So this is really nice and gives us our idea for the proof, that is induction over the number of vertices. But we see that there is indeed a problem with this approach. So if v were not in this graph and we would find a nice partition of the other vertices and add it back in to the set where v knows an even number of vertices, then the property would be satisfied for v, but all of the vertices that know v and are in the set that v was added to will then have an odd degree, which means that this does not work. So to get a better feeling for how this idea might work, let's try to do induction just as I have described on this graph right here. So let's redraw it one more time. This is our given graph. This is the vertex v, and we are going to transform it into a new graph by just removing the vertex v from it. This gives us a new graph, which we are looking for some partition on to then do the induction. But I'm going to redraw this in a much nicer way for our partition. So this is nothing but those two vertices right here and something like that. These two graphs are isomorphic, and this gives us really the way to do the partition in this way. So in our original setting, that would mean that both of these vertices are in one set and all of the others in the other one, and then indeed everybody knows, in this case, 0 other persons in his room, which is an even number. Now, as described earlier, we take a look at the neighbors of v. So this is the green set. And of course, since v has an odd number of neighbors in the original graph, this set has also an odd number of vertices, and therefore there exists one of those two partitioning sets where an odd number of neighbors of v is in. And in this case, this is not the orange set because two of the neighbors of v are not colored orange. Therefore, by what I've described before, our partition for the original graph will look like so. So because V knows an even number of vertices from the non-orange set, we're not going to add V to the orange set, which gives us something like that. But we see that this partition does not work because all of the neighbors of V that are in the set that V was also added to, namely those two right here, now have an odd degree inside their set because they are now, before they had an even degree, but now V was added to their set, therefore they both have an odd degree, which means that this induction does not work. But we can transform this approach into an induction which indeed does work. Because we need to do some clever manipulation to our new graph besides removing the vertex V. We also want to make use of the property that the set that V gets added into has exactly an even number of neighbors of V, whereas the other set where V is not added into has an odd number of neighbors of V. So the general idea was to remove V, then use induction to get a partition on the smaller graph, and then add V back in. Now we could do another manipulation to our smaller graph to make all of this work. And one idea that we could get is to manipulate the edges between neighbors of V. Because if we imagined that besides from removing V from this graph, we also added back in this edge, for example, this is not going to work exactly, but just go with me for now, then we would have this edge in this graph, and both of those would have even degree still. But then, if we transform back to our original graph, if we removed some edge, then that would make those edges have odd degree, but then adding back V in again, those two effects would cancel out. So we are searching for a second transformation that we can do simultaneously that exactly cancels out with our problem that if we back in V into one of those sets, that all of its neighbors in that set get odd degree. And I'm going to present what approach works out nicely right here. So firstly, we remove V, and secondly, we swap the relationship of x, y, and e for x, y neighbors to V. I'm going to demonstrate why this is a good approach on our example graph. So that looks like. So we want to remove the vertex V from it, and therefore we will only be left with a graph consisting of 5 vertices. All of the relationships between vertices where at least one is not a neighbor of V stay the same, but the edges between neighbors of V get flipped. Therefore, we remove that edge and instead add those two new edges to the graph. By our induction hypothesis, we can find a way to partition those vertices into two sets such that our condition holds. And indeed, of course, this is the case here. In particular, we partition the vertices like so. And from that, we want to get a good partition on our original graph. Now we take a look at the original neighbors of V, and we see that 2 of them lie in the left set. Therefore, by our idea, we're going to add V to the left set exactly, and this gives us the same graph as before, but with a partition. So yeah, I'm going to redraw all of those vertices, and V is going to be on the left of this line that I will draw in right now. Of course, we are not dealing with our modified graph any longer, so we have to draw in the original edges and get that graph. And indeed, this worked out really nicely, because by construction, of course, V has an even degree inside its set. All of the non-neighbors to V also must still have an even degree because they had an even degree before. All of the vertices that are neighbors to V but lie in the other set are going to be considered next. We can verify that reverting that operation and putting V into the set where it has an even number of neighbors maintains our desired condition. Indeed, that must be true for V by definition because it does have an even number of neighbors inside of its partitioning set. Furthermore, this is also clear for any vertex that is not V, but also not a neighbor of V. So we call the set of vertices that are adjacent to V n of V. So we consider some vertex that is neither V nor a neighbor of V. So by our inductive hypothesis, it had even degree before reverting our operation. But doing so doesn't change the edges incident on it. So it also has even degree afterwards. Lastly, we're going to deal with the set of neighbors of V. To do that, let's introduce the partition set A, which is that which contains V, and call B the other one. We consider some neighbor of V, which should also lie in B. Now, reverting the operation flips all edges between W and some other vertex in n of V. But only those flips contribute to a change in degree of W within B, where the other endpoint of the edge also lies in B. So, the number of such flips is 1 less than the size of that set, which is equal to 2k plus 1. So the parity of the degree of W within B is changed 2k times, which is even. And since W had even degree to begin with, this is good. Now, for some U in n of V intersected with A, we get that this set has size 2L, and therefore there are 2L minus 1 elements of this set not equal to U, so we have 2L minus 1 flips that each change the parity of the degree of U in A, but this is very good and exactly why we constructed this operation in that way, because we also add an edge U comma V. And therefore, in total, we change degree of U 2L minus 1 plus 1 times. Therefore, because vertex U had even degree to begin with, it also has even degree now. This finishes the proof of our inductive step. We already established a base case, which is any graph where all vertices have even degree. So in any case, we are done.